We may have misunderstood the universe. Those are not my words. They belong to Adam Riess, a Nobel Prize-winning physicist at Johns Hopkins University. A man who has spent his career measuring how fast the universe is expanding. And he is not being dramatic. He is looking at the data and saying, very plainly, that something in our model of reality does not add up. For nearly a century, cosmology has rested on a single elegant framework. The Standard Model. A set of equations and assumptions that describe everything from the first fraction of a second after the Big Bang. It has worked remarkably well. For decades, it explained observation after observation with an almost suspicious level of precision. It predicted the cosmic microwave background. It predicted the abundance of hydrogen and helium. It described how galaxies cluster across billions of light years. Each time we tested it, it held. And then the James Webb Space Telescope turned on. What Webb found did not confirm our understanding. It complicated it. In some cases, it contradicted it. And the deeper we have looked, the wider the cracks have become. The trouble begins with a number. The Hubble constant. It measures how fast the universe is expanding right now. Not in the past. Not in theory. Right now. At this moment. You would expect a number like that to be straightforward. 2 methods. 2 teams. Same universe. Same answer. That is how science is supposed to work. But it did not. And this is not new. The Hubble constant has been a source of disagreement since the 1920s, when Edwin Hubble first calculated it. His estimate was so far off that it implied the universe was younger than the Earth. For decades after that, astronomers argued. Was the value closer to 50? Or closer to 100? The disagreement was intense. It split the field. By the early 2000s, it seemed resolved. The number converged. Roughly 70. Close enough. The problem appeared solved. Except it was not. Because as instruments became more precise, a new discrepancy emerged. Smaller than before. But far more stubborn. The first method looks backward. Far backward. The Planck satellite mapped the cosmic microwave background. The faint afterglow from when the universe was about 380,000 years old. From that map, physicists reconstructed the conditions of the early universe. They fed those conditions into the Standard Model, then ran the equations forward nearly 14 billion years. The result was precise. About 67 kilometers per second per megaparsec. A megaparsec is about 3.26 million light-years. So for every 3.26 million light-years you look outward, galaxies move away 67 kilometers per second faster. A clean number. A tiny margin of error. Confidence is extremely high. The second method works differently. It measures the present. Led by Riess, scientists built the cosmic distance ladder. They start with Cepheid variable stars. Stars whose brightness fluctuates in a predictable way. Measure the pulse. Determine the intrinsic brightness. Compare it to how bright the star appears. That gives you distance. From there, they step outward to galaxies containing both Cepheids and type Ia supernovae. Supernovae explode with nearly identical brightness. Once calibrated, they can be used across vast distances. Combine distance with recession velocity, and you get the expansion rate. Their result was not 67. It was 73. That difference is not small. In cosmology, measurements are often precise to within 1%. An 8 to 9% gap is enormous. It changes everything. The age of the universe. The size of the observable universe. The rate at which galaxies separate. Even the nature of dark energy. If the expansion rate is higher than predicted, then every downstream calculation shifts. You are not adjusting a parameter. You are redrawing the entire history of the universe. For a while, scientists assumed there must be an error. The leading explanation was stellar crowding. Cepheid variables often sit in dense, dusty regions. Light from nearby stars can blend together. That makes them appear brighter. Brighter stars appear closer. Closer distances imply a higher expansion rate. If that blending could be corrected, the tension might disappear. So Riess turned to Webb. Webb orbits about 1.5 million kilometers from Earth, far beyond atmospheric interference. Its 6.5-meter mirror observes in infrared, cutting through dust. If any telescope could resolve this, it was Webb. The expectation was clear. Sharper data would reveal the error. Distances would adjust. The Hubble constant would drop. The tension would resolve. That is not what happened. Webb confirmed the measurements. Not approximately. Almost exactly. The Cepheids looked the same. The distances held. The expansion rate remained at 73. In early 2024, the JWST team published results extending Webb observations to galaxies like NGC 5468. Thousands of Cepheids. Multiple supernova hosts. The conclusion was clear. Measurement error could be ruled out. Rias said it plainly. If the errors are gone, then we may have misunderstood the universe. At a conference, he asked David Gross whether this should be called a problem. Gross corrected him. Not a problem. A crisis. And by late 2024, that crisis had deepened. New data did not soften the discrepancy. It reinforced it. Multiple independent methods, applied to the same galaxies, produced the same result. Cepheids. Carbon stars. The tip of the red giant branch. Different techniques. Different assumptions. Same conclusion. The expansion rate of the universe appears higher than the standard model predicts. At that point, the question became unavoidable. If the measurements are correct, then what is wrong? There are only a few possibilities. The first is that something in the early universe is missing from our model. Not something large. Not something that would overturn everything we know. But something subtle. Something that changes the expansion history just enough to matter. This is where the idea of early dark energy comes in. A hypothetical component. Present only for a short period after the Big Bang. Then gone. If it existed, it would slightly alter the density and pressure conditions of the early universe. That, in turn, would affect the evolution of the cosmic microwave background. And, ultimately, shift the predicted expansion rate. It is an elegant idea. Because it preserves most of the standard model. It does not require a complete rewrite. Only a small adjustment. But there is a problem. There is no direct evidence. No detection. No independent confirmation. It exists as a possibility. Nothing more. The second possibility is that the issue lies in the late universe. In how we measure distances. In how we interpret light. In how we construct the cosmic distance ladder. This is less dramatic. But more difficult. Because it means questioning tools that have been refined for over a century. The cosmic distance ladder is built step by step. Each rung calibrated by the one below it. Cepheids. Supernovae. Red giants. Each method depends on assumptions. About stellar behavior. About environments. About calibration. And small differences in those assumptions can lead to measurable differences in the final result. This is where the work of Wendy Friedman becomes important. Her approach relies less heavily on Cepheids. She uses red giant stars, and another class known as JWST stars. These stars are found in less crowded regions, less affected by dust, less affected by blending. When she applied her methods to data from the James Webb Space Telescope, the results did not fully agree with either side. Some measurements aligned with the standard model. Others leaned toward the higher expansion rate. The combined results sat in between, around 70. That might seem like a compromise, but it introduces a different problem. Because now the disagreement is not just between early and late universe measurements. It exists within the late universe methods themselves. That suggests something deeper. That the tools we rely on may have limitations we do not fully understand. The cosmic distance ladder is powerful, but it is not perfect, and no single telescope can fully eliminate those limitations. So the debate continues, not because there is no data, but because the data does not converge. And that is where things become interesting. Because when independent methods disagree, it forces a deeper question. Not which one is correct, but whether the framework itself is complete. And the Hubble tension is not the only place where this happens. The early universe presents another challenge, one that arrived almost immediately after Webb began observing. Galaxies. Not small ones. Not primitive ones. Large. Bright. Structured. Seen at redshifts corresponding to just a few 100 million years after the Big Bang. At that stage, the universe should still have been in its early phases of structure formation. Galaxies should have been small. Irregular. Still assembling. But instead, Webb revealed systems that appeared far more developed. Some comparable in mass to the Milky Way. That should not be possible. Not within the standard timeline. Because galaxy formation is not instantaneous. It requires gas to collapse, stars to form, feedback processes to regulate growth, mergers to build mass. All of this takes time. And yet, these galaxies appeared early. Too early. The initial reaction was concern. If these observations were correct, then our understanding of galaxy formation was incomplete, or the cosmological model needed revision. Some early interpretations suggested extreme efficiency, nearly all available gas converting into stars. That is not how known physics behaves. In typical galaxies, only a small fraction of gas becomes stars. Most of it is heated, expelled, or remains unused. These early galaxies appeared to violate that pattern, which raised the possibility that conditions in the early universe were different. Denser, more favorable for star formation, more efficient. But before that conclusion could be accepted, a correction emerged. Some of these galaxies were not what they seemed. They contained active black holes, accreting matter at high rates. As matter fell inward, it heated up, and emitted large amounts of radiation. That radiation blended with the light of the galaxy, making it appear brighter. And brightness is often used as a proxy for mass. So, a galaxy that appears bright may not actually be as massive as it looks. This effect was significant. Once these systems, sometimes called little red dots, were removed from the sample, many of the most extreme cases disappeared. The tension eased, but it did not disappear. Even after corrections, there were still more massive galaxies than expected. Not enough to break the model, but enough to strain it. Enough to suggest that something about early star formation is not fully understood. And then came another observation. A massive spiral galaxy, formed within the first 2 billion years of the universe. Spiral structure is not trivial. It requires relatively stable conditions, ordered rotation, time. In a young universe, galaxies are expected to be chaotic, merging, disturbed. Yet this galaxy appeared organized, structured, mature. That does not fit easily within the standard picture. At the same time, other observations showed the opposite. Chaotic systems, clumpy structures, irregular shapes. So the early universe contained both extremes, disorder and structure, side by side. And then there are the elongated galaxies, systems that appear stretched, prolate, aligned along filaments. These shapes are not random. They follow patterns that do not match predictions from cold, dark matter, but do align with alternative models. Warm, dark matter, wave-like dark matter, models where particles are lighter, where structure formation is smoother, where matter flows differently. This matters because cold, dark matter is not just a detail. It is the backbone of the standard model. It determines how matter clusters, how galaxies form, how large-scale structure emerges. Change that, and you change everything. The distribution of galaxies, the formation of clusters, the behavior of gravitational lensing, the evolution of cosmic structure. It is not a small adjustment. It is foundational. And then that brings us back to a broader realization. We do not fully understand most of the universe. Dark matter makes up about 27%. Dark energy about 68%. Everything we can see, stars, planets, gas, accounts for only about 5%. The rest is inferred, not observed directly, not measured in a laboratory. We know it exists because of its effects, not because we have identified its nature. So when observations do not match predictions, it may not be the observations that are wrong. It may be our assumptions. There is also another discrepancy, less visible, but persistent. The state tension. It concerns how matter is distributed, how clustered the universe is. The standard model predicts a certain level of clustering. Observations consistently show slightly less, not dramatically less, but consistently lower. And consistency matters, because when independent measurements point in the same direction, they form a pattern, and patterns suggest underlying causes. So now we have multiple tensions. The Hubble tension, the early galaxy problem, the state discrepancy, the shape of galaxies. Individually, each one can be explained. Collectively, they are harder to ignore. They suggest that something is missing. Not necessarily wrong, but incomplete. And that distinction is important, because incomplete models are not failures. They are steps. They describe what we know, and point toward what we do not. The standard model still works. It explains the cosmic microwave background. It predicts elemental abundances. It describes large-scale structure. No alternative model matches its success, but it has limits, and those limits are becoming visible. This is not unusual in science. It has happened before. Models reach a point where they no longer explain everything, not because they are wrong, but because they are not complete. Newton's laws described motion with extraordinary accuracy, until we looked at extreme conditions. Then relativity became necessary. Classical physics described energy and radiation, until quantum effects became visible. Then a new framework emerged. Each time the transition was not immediate. It was gradual, driven by small discrepancies, persistent ones. And that is what we are seeing now. Not a collapse, but a transition, a shift, from one level of understanding to another. And that shift is driven by data, by observation, by the simple fact that the universe is more precise than our models. We are measuring reality with increasing accuracy, and reality is revealing its complexity. Not dramatically, not all at once, but gradually, piece by piece, and that is what makes this moment significant. We are not speculating. We are not guessing. We are following the data, and the data is telling us something. It is telling us that our picture is incomplete, that there is more to learn, more to discover, more to understand, and that is where science becomes most interesting. Not when everything fits, but when something does not, because that is where new ideas emerge, new models, new frameworks. And right now, we are at that point, not at the end of understanding, but at its boundary, looking at something that does not fully fit, something that resists explanation. And that is where progress begins. Because the universe is not obligated to match our expectations. It only has to be consistent with itself. And if our models fail, it means we have more to learn. And that is not a weakness. It is the strength of science, the willingness to question, to adapt, to revise, and to continue, even when the answers are unclear, even when the data is uncomfortable, even when the picture does not make sense. Because somewhere in that uncertainty, there is structure, and somewhere in that structure, there is an answer, and we are getting closer to it. The universe is not breaking, it is revealing. And what it is revealing is that our understanding is still incomplete, not wrong, not broken, but unfinished. And the next version, whenever it arrives, will not just resolve a discrepancy. It will expand the way we understand everything.